Okay, here is part 2 of our theorems packet, where we're going to talk about the mean value theorem. Okay. Now, just like the intermediate value theorem was all about making the function equal a number, the mean value theorem, you can kind of have an idea that you might be using mean value theorem if you're trying to let or figure out where f prime of a function equals something specific. Okay? And the thing that f prime is going to equal is it's going to equal the slope between two numbers. Okay? What I'm showing you over here is if we have 2 points A and B, and we calculate that slope, okay, we calculate the average rate of change, f of B minus f of A over B minus A, whatever number we get. The intermediate value theorem, or excuse me, the mean value theorem says that somewhere between where that A and B are, there's another point on the curve where if I do a tangent line, that tangent slope is the same as that average rate of change slope. Kind of the thing we say a lot for mean value theorem is we talk about that the average rate of change is going to equal the instantaneous rate of change. As long as we're talking about a continuous function and the differentiable function. So it doesn't it can have endpoints, okay? So it doesn't have to be differentiable at the endpoints. It has to be continuous, over the closed interval, differentiable. So the derivative has to exist. You have to be able to find the instantaneous rate of change everywhere between A and B. Now, in a lot of mean value theorem problems, they basically say, hey, find the special number that satisfies the mean value theorem. So when we're looking at that, like we see here on these two examples, basically you're looking for trying to show or make the instantaneous rate of change equal the average rate of change. Show where that's going to happen. Solve that relationship. Find this number that will make where the instantaneous rate of change will be the same as the average rate of change. Now, first thing I'm going to do on problem 3, I don't know why we wrote problem 3 like a product, because that's actually kind of lame. It's a really easy product to do. So I would not probably do product rule on that. So here's my function f of x. And if I calculate the average rate of change of f of x on the interval from -1 to 1, that means I'm looking at f of 1 minus f of -1 over 1 minus -1. And so take a little arithmetic break here. F of 1 is going to give me -2. F of -1 is going to give me 0. And so my average rate of change value is -1. So that means I should be able to make f prime of x equal -1 somewhere between the x's of -1 and 1. That would be the mean value theorem result. There it is. I write too big. Okay. So I figured out my average rate of change was -1. Now I'm going to set my derivative, f prime, equal to -1 and solve and show that my solution is going to be in here. Okay. So f prime is 3x squared minus 2x minus 2. The 3x squared minus 2x minus 2 should equal -1. That should have a solution. And wait, let me back up for a second and double check something. Yeah. This actually, where we're going to make it equal it, it's going to equal it on the open interval. We're not going to consider the endpoints as a possible place where this could happen. So this will have a solution on the open interval -1 to 1, not the endpoints. All right, so 3x squared minus 2x minus 1 equals 0. If I add 1 to both sides, I had to be real careful though, I'm going to start at minus 3. Factor, factor. 3x minus 1 minus 3 plus 1. So, oops. Okay, yeah, that's not the right math. -1/3, 1, but I can't use this because that was an endpoint. So, the number I figured out, solution is x is -1/3. I don't know why I keep writing -1/2 or -1/3. Because I'm dumb. And that means that f prime of x equals -1 at x equals -1/3, which is what the mean value theorem said should happen, is that there's a number in between -1 and 1 where the derivative will equal the average rate of change between -1 and 1. There's a lot of calculations, a lot more calculations in average rate of change, instantaneous rate of change comparison here, because we have to do the average rate of change. We have to do the instantaneous rate of change, and we have to solve. That's kind of the bad news. The good news is a lot of mean value theorems say, hey, use the mean value theorem to show this that this will work, or show that the mean value theorem applies. And when you see mean value theorem, you're automatically going into, all right, that means average rate of change, instantaneous rate of change, take my derivative, function inside it equal to the value that's the average rate of change. All right, so problem number 4 and problem number 5 are both applications of the mean value theorem. Problem 4 is exactly what we did on number 3. Problem number 5 is the same thing. Find the mean value theorem number, C, in the interval. So it would be a good point right now to stop here, do number 4, and then maybe turn this back on and check, and then do number 5 and turn it back on and check. Because the process on 4 and 5 are exactly the same as the process on 3. We're going to look at the derivative equaling the average rate of change. Okay. So I'm going to continue. I'm going to do those two. Like I said, this would be a good place for you to stop and try this yourself and then check. Okay. All right. So what has to happen is that the cosine of x is going to equal the sine of pi minus the sine of 0 over pi minus 0. And if you know your unit circle, sine of pi and sine of 0 are both 0, so the average rate of change is 0. So I'm looking for the cosine of x equaling 0. And once again, if you know your unit circle, that would have to happen if we're restricted to looking at 0 pi. That would have to happen at pi over 2. So actually, that trig one was a lot easier because we didn't have all this much arithmetic. As long as you knew your sine curve and your cosine curve and your unit circle, numbers were a piece of cake. Now, when I look at problem number 5, which is from the BC test in 1988, mean value theorem usage means the special magic number can't be at the endpoints because we're looking for a number in the open interval 0 to 2. So, bam, bam, can't be either of those guys. So we should be looking at f of 2 minus f of 0 over 2 minus 0. And here's my f of x. So f of 2 is going to be 0 minus, oh, look at all these zeros. So 0. So f prime of x equal to 0 around the interval 0 to 2 is what mean value theorem says should happen. 3x squared minus 4x equals 0. X, 3x minus 4. It can't be x equals 0 because of the restrictions off the endpoints. So, bam. Like I said, if it's a one where they say, hey, use the mean value theorem, you've got an attack process. Okay, mean value theorem, average rate of change, instantaneous rate of change, set them equal to each other. Tangent line. Every time we do a tangent line, you know we need a point and we need a slope. The slope is going to come from f prime of x. The point, this is what they don't tell us in this problem. So the point we need is the mean value theorem point. Okay. So that means we need the point where f of pi minus f of 0 over pi minus 0 equals f prime of x. That's how we'll get the x of our point. Y for our point? Original function. Okay, so let's see. So my f of x is 2x. So this would be a good point to stop. Now that I've kind of set you up with what we have to do, stop and see what you can get. I found my derivative, and I'm going to find my average rate of change. So f of pi is going to be 2 pi plus 1 minus 1 over pi, which is 2. Ooh, this is going to be so awesome. Cosine x plus 2 equals 0. No. I'm thinking ahead. Cosine 2 plus x equals 2. So cosine x equals 0. So x must be pi over 2 in our interval. So this is going to be the x of the point where the tangent line is. Let's get the y. put this back in the original equation. So it's going to end up being pi plus 2. And so pi over 2 for x, pi plus 2 for y. And my slope well, it has to equal 2. I mean, you can take the derivative and plug in pi over 2 again, but you're going to get 2. I mean, that's basically what we said. It's like where we are, the slope is 2, and we're just going to write the full equation with the line. So y minus the quantity pi plus 2 equals 2 times x minus pi over 2. And tangent lines are never going away. Tangent line equations, a big application for us. Alright, so that's the end of the mean value theorem part. I'm going to continue now talking about Rolles' theorem, because Rolles' theorem is just a special version of the mean value theorem. The only thing that Rolles' theorem is about is, since it's talking about the time when your 2 points A and B have the same y value, that your average rate of change comes out to be 0. So you have to show that your instantaneous rate of change, figure out where that's going to equal 0. So Rolles, I don't know if that was a person, I have to look that up. I say that every year. Rolles kind of like just took the mean value theorem and talked about one little special case of it. It's the special case of the mean value theorem when we're talking about an average rate of change and an instantaneous rate of change equal to 0, because the y value of the x's on the interval are equal to each other. If you're using Rolles' theorem, but you say you're using mean value theorem, that's fine. Mean value theorem is a more generic version. If you say you're using Rolles' theorem, you should be specifically looking at a situation where when you did the average rate of change, you got 0. I don't know that I've seen a question specifically about Rolles' theorem where it says the words Rolles' theorem. If we would happen to see that, then you have to just kind of say, okay, that's right, mean value theorem with 0 in there. Okay. Once again, we have to meet the criteria though. We have to be continuous on the closed interval, differentiable on the open interval for Rolles' theorem to work. Okay, so the first thing to do is to figure out if, in these problems, these are just some examples, is this really a Rolles' theorem problem? Okay. And I'm going to tell you right now, on number 7, even though f of 1 is going to be 0 and f of negative 1 is going to be 0, so the average rate of change is going to be 0. This is not a Rolles' theorem problem. It fails to meet a condition. Before we worry about the average rate of change being 0, we have to make sure we've got the continuity. So I'm going to leave this as an open-ended question. I will write it. No, I'm going to go ahead. Well, continuity fails on negative 1 and 1. I'm going to leave that open for you to think why. And if you're not sure why, that needs to be something to come back and talk to me about. Why is this function, where, I guess is a better way to ask that, where is this function not continuous over the interval negative 1 to 1? because we're not continuous at that number, within the interval, we can't use Rolles' theorem over the interval. We can't use mean value theorem over the interval. We can't use intermediate value theorem over the interval. Right? All these theorems require continuity. Now, problem number 8. Is this a Rolles' theorem problem? Well, polynomial, continuous everywhere, so definitely continuous on the interval, so we met the conditions. F of 2, let's see, like be 16 minus 8. F of negative 2 would be 16. Okay, so yes, this is a Rolles' theorem problem. F of 2 and F of negative 2 are the same, so average rate of change would be 0. We have to show or find where f prime of x would equal 0 on negative 2, 2. So f prime of x equals 4x cubed minus 4x. 4x cubed minus 4x equals 0. X squared minus 1 equals 0. And we've got multiple places, multiple solutions. X equals 0, x equals 1, x equals negative 1. At all 3 of those places, f prime of x equals 0. This is the theorem that gives us critical values. That's what it means when we say we have the critical value for f, is the f prime is equal to 0. F prime equal to 0 is exactly what we're looking for here. So on this function, there are 3 places between negative 2 and 2 where f prime equals 0. 3 critical numbers from negative 2 to 2. Is that all it said, just to find them? Yeah. Values, I guess we should have. Alright. Okay, so show that Rolles' theorem holds true within this function and find the value of c. Alright, so I need to find 2 points on the curve with the same y values, because that's how that's going to happen. Well, if x equals 1, no, that's a lie. If x equals 3, y will be 0. If x will be 0, y will be 0. That's kind of a good generic y value to see. If both my y values are 0, then f of b minus f of a is going to be 0. Okay, so the 2 points we're talking about are 3, 0, 0, 0, which means we're going to show on the interval 0 to 3, f prime is going to equal 0. This is definitely a harder problem because it doesn't tell you kind of, well, where should you be looking? Where's the Rolles' theorem part? And you had to definitely think more about figuring out the interval. Now, f prime 2x minus 3, this is the easy part, 2x minus 3 equals 0, x equals 3 halves. So the value of c is 3 halves, where Rolles' theorem applies. You have a homework paper, or you're going to have a homework paper, that involves intermediate value theorem, mean value, and Rolles' theorem. There are ways to kind of trick you when you're looking at those. If it's, and so that's always going to be our first, is what are we trying to show? What theorem are we trying to work with? Both theorems end up with the idea that we're trying to show that we can achieve a certain y value from an x value in an interval. Question is it just sort of any old y value that we're trying to show that the function equals, or are we trying to show that it's the average rate of change value that the derivative equals? I'm going to stop this video here, and I think on the third video, I'll do the extra practice problems. Okay? All right, so that's all for now.